Hello, my name is Dr. Stephen Schmid and I'm presenting our research understanding shock event cavitation injury. This is research I conducted with the Australian Army Lieutenant Colonel Matthew Brooks. The idea is that we are aiming to predict, prevent and detect shock event cavitation injury. Now this is where a high pressure shock wave from either a blast, bullet impact, blunt force or weapon system overpressure travels through the body, and behind it a area of low pressure causes the liquid in the body to vaporize and form a cloud of cavitation bubbles. Then as the shock wave continues to travel, the cavitation bubbles collapse and cause damage to the body. The origin of this research was observation conducted during terminal effects testing of in-service Australian Army bullets, both 5.56 and 7.62, conducted up at Greytown, the Joint Proof and Experimental Unit. Matthew Brooks conducted this research. So what we have here is a bullet travelling through clear ballistics gelatin, shown by the yellow arrow, and a cloud of cavitation bubbles forming well in advance of the bullet. I'll show you a video of this event now occurring. And you can see the bullet enter on the right, the shockwave travel through, and the cloud of cavitation bubbles occurring on the left. Other cavitation effects include sonoluminescence. Now this is where the bubble collapses, and inside the bubble the temperature can reach 2 million degrees Kelvin, which we believe may lead to the bubble being reheated, leading to greater re-expansion. And here is a video of this occurring, generated in the laboratory and slowed down 1 millionfold. The amazing thing is, as the bubble collapses, it actually sonoluminesces and emits light. Another effect is called dieseling, where elements of the surrounding tissue, in this case, in the video, it is clear ballistics gelatin, but in the body, it may be fats or other tissues, which could, through their combustion, lead to toxins being generated. Now this effect is called dieseling, and in the video you'll see a 5.56 round causing this dieseling effect with black toxic smoke ejected from the gelatin. So the bullet will enter from the left this time, passes through, a void opens up, and there you have the dieseling effect with the combustion, and out of the entry wound comes the black smoke. So within the body, this may happen at a miniature scale within each of the hundreds of cavitation bubbles that may form in the body. Now, this also happens, these cavitation bubbles occur in nature. Here is a small 1 inch long, 25 millimeter long pistol shrimp that through its specialized claw actually creates a cavitation bubble which collapses, sonoluminesces, and sends out a 200 decibel shockwave, which the pistol shrimp uses to kill prey at up to 1 meter from itself. Now within defense, other researchers are linking and making the case that there is a link between cavitation injury and neurodegenerative disorders such as post-traumatic stress, and including nerve and other damage remote from small arms entry sites. Potential cavitation injury hazards in defense are blast, bullet, blunt force, including concussion, electromagnetic and weapon system overpressure. In the US military, post-mortems have been conducted on brains of veterans and have actually shown damage to the brain from overpressure, including chronic traumatic encephalitis, the Boxer disease. And in the US Army, anyone caught within 50 metres of blast is actually screened for traumatic brain injury. However, due to the operation impacts, this requirement is often ignored, and therefore we will actually aim to provide better guidance on the risk assessment exposure for cavitation injury. And shown here is the traumatic brain injury researchers around the world, including those currently also looking at blast-related cavitation injury. So the current program of research is prediction using empirical and numerical models. And to validate our models, I conducted and developed empirical equations for cavitation, then allowing for non-Newtonian, so shear thickening behaviour of both ballistic gelatin and human tissue, validated my numerical model as shown on the bottom of the diagram to experimental results developed by the US United States Naval Research Laboratory. And the numerical model was able to predict the same behaviour and same cavitation locations. The interesting thing is that as the shear thickening behaviour is shown, numerically we are finding that less pressure was required to initiate cavitation with more shear thickening materials, such as in the brain and in the body, versus the experimental. The difference we found is that the numerical results were able to pick up very small micrometer diameter bubbles at the critical pressure, versus the experimental results, which, due to their visual observation, were only picking up 1 millimeter size bubbles. The next series of experiments proposes to actually use a microscopic camera to be able to pick up the much smaller bubbles, and hopefully, or we predict that the results were actually aligned between the experimental and the numerical at the much smaller bubble size. I also modelled small arms and compared them to the results obtained at the terminal effects testing as shown in the original video, and I was able to show that same behaviour, including shockwave propagation and shockwave reflection within inside the ballistic gelatin, and the yawing behaviour of a bullet as shown on the top right when spin is applied to the bullet. Within the human body, I modelled a 50th percentile torso and determined that the lowest pressure for cavitation occurred at 30 megapascals, so about the equivalency of a sledgehammer blow. And at this low pressure, cavitation occurred in the front of the model, so that is in the shoulders and in the hips. The aim now is to prevent the cavitation injury occurring by developing advanced body armours and helmets. So the aim was to first determine the maximum pressure that occurred behind the top layer tier 3 armour at the critical velocity for a 5.56 round. And here's our numerical model showing the bullet impacting, and from this we're able to determine the back of armour pressures. So here we have the bullet impacting in the model on the top left, showing the same behaviour as experimentally as shown in the top right. And at the back of the armour we actually achieved, was shown to have 101 megapascals of pressure, which is above the critical pressure for the torso, which was the 30 megapascals. So it appears and is predicted that cavitation will occur behind the in-service tier 3 armour for a 5.56 round, impacting at 600 meters per second. Even at this range, it means that the armour will not protect the human from cavitation injury, even at various entry angles and out to the effective range of the weapons. To reduce that pressure to below the critical pressure of 30 megapascals, it's proposed to actually have a new layered armour with a thin silicon sheet as the first layer, so the same ceramic material as the Tier 3 armour, but then have a liquid-filled bladder behind it. Now, bullets are designed to break up and fragment when they hit the body. They feel the liquid pressure. Now, this is by design, so the bullet doesn't pass through the body, but in fact imparts all its kinetic energy into the body to damage the body. Here, we actually use that design against the bullet to defeat it by presenting it with liquid beforehand, causing it to fragment and dissipate its energy into the liquid, and then the edges of the liquid bladder burst at below that critical 30 megapascals. Here we have then another layer of ceramic behind that to stop the last bit of fragmentation, and some high density foam to give a final deadening of that impact. The advantages here is we actually get in a new design, not much thicker than the original 15mm armour, the same protective effect for both penetration, a improved pressure distribution, and a weight saving of around 40%. Further, by replacing the high density foam with a second burst bladder, we may actually be able to provide the first ever multi-impact, multi-round armour. And here we model the effect of that pressure wave being transferred rather through the body but outwards within the liquid layer and out to the seams. And here is a mock-up showing a mock-up of the extant armour made out of the silicon carbide. In this case, it's a mock-up, and the multi-layer on the right, showing the different layers. And this is a full-size mock-up of what the armour would look like. Finally, prediction. We're using a full-body digital model of the human, a digital twin. We would apply various forces to the body to predict where the cavitation injuries may occur, and then be able to provide that advice to medical staff and radiologists to go looking for the characteristic circular bubbles throughout and scarring throughout the body. We prevent this also from occurring by applying our body armours and helmets, and detect it utilising image recognition software to analyse medical imagery. And here it's small squares would go around that scarring as shown by the red arrows, and also recalibrating the in-service pressure sensors to detect that critical pressure of 30 megapascals. In the future, we aim to redo the initial testing for those smaller bubble analysis using the microscopic lenses, and also redo full-size testing of human brains and other body parts in conjunction with the Netherlands Organisation for Applied Science called TNO, utilising the facilities as described above. In the images below, current testing is done through cadaver studies, so real human brains, but unfortunately they only have a usable lifespan of about 2 to 4 hours before they start degrading, where we would use a numerical model shown in the centre and a full-size 3D printed version of the human body as a mould to make ballistics gelatin moulds of the human skull to test at full scale. Prevention, we would optimise the advanced body armour, conduct proof of concept testing including helmets, and even test for the multi-hit protection using 2 or more burst bladders in the armour. We'd also determine exposure limits for blast, weapon system overpressure and concussion, including return to play. And an outcome may be better guidance to the operators for when soldiers should really be taken off the battlefield to be tested for cavitation injury and concussion, and potential guidance on exposure limits for weapon systems down to 50 cal sniper rifles, and recommendations for things like utilisation of remote weapon systems for artillery. In the detection realm, our cavitation injury image recognition software to aid radiologists, and a potential to compare pre and post deployment scans to see if military personnel have actually had cavitation injury during deployment. Our in-service blast sensors to give further indication. And finally, lethality and survivability modelling to determine the risk of cavitation, including weapon system lethality assessment and the potential to actually increase lethality of weapon systems. Finally, return to play guidance may be provided, along with survivability guidance such as already exists for overpressure for lung injury, as shown on the right. And implications, concussion, including contact sports and falls, especially in the elderly. And this is a study conducted by the US Army, and it shows effectively the same sorts of concerns that we have also had. So with this, cavitation injury may actually be the answer for the specific causal mechanism. Our team is Schmid Research and Development, Glide Diagnostics, who specialise in traumatic brain injury, Sabre Astronautics, who are an image recognition software specialist, and Advanced Analysis Australia, who are blast modelling specialists. Finally, the benefits to vents is to be able to predict cavitation modelling, cavitation injury, including full body models, command guidance, standard operation procedures, and weapon system lethality modelling. For prevention, we're aiming to provide advanced body armour and helmets and exposure limit guidance to operators. And finally, cavitation injury recognition software and pressure sensors for the detection of cavitation injury. And these are my details for further information. Thank you very much.